last time we were talking about the shear stress in the beam. It says that if we have these things and we put the transverse load like that, you see, they sleep on top of each other. So it says that why they sleep and the interface, why they move along the interface, there should be some load along that interface that cause them moving along the interface, so they're not going to stay in the same position. So we start to talk about it. If there is a horizontal force in the interface, so there's going to be the horizontal shear in the interface. So we talk about it, how we can find that horizontal shear or horizontal shear force. But we know that when we put the vertical load on that, it's going to be like I'll give you an example. Put a knife on the bottom. There should be also a vertical shear there. So the vertical shear there, we know that because it's going like that, and want to cut it like that is there. But this shows there are going to be also the horizontal. So last time we just started to talk about it and say, okay, how we can find the horizontal load at that interface. So if I have that and I cut it there, and let's see, okay, what's happening here? We find it what's happening here along that. Now I want to see what's happening here along that interface. So so if you have a beam, simple beam again like this. And there's going to be a load applying on the end. Force applying on that. If I go ahead and say, hey, I want to see what's happening at any, for example, given section. So for example, here, if I go here and say, assume this is the CC, I want to see what's happening there. So I'm going to split it in two. So then I have the left side of that. And I have the right side of that. Let's see. This is going to be the F here again. And then I'm going to have the internal forces. It's going to be the V and the M. So I'm going to have these. So I have V, M, and P, and P. So I have them. So now I do have them, so I know that there's going to, that shear is going to be vertical shear. There's going to be a shear on that interface because it's going to cut it right in the middle. So if I go ahead and I'm going to draw that section, that CC section, a little bit larger so we can see that. So this is my cross section. At point C. So I said, assume this is CC section. And then I know that I have the vertical shear there. That's the vertical shear going down. And then so I have that vertical shear going down, at that interface, so I know that it's going down there, so it's going to be the V going down there. And then assume I want to go ahead and cut it. I want to find the shear at this point, at this interface. So it's the A, and that's the B. I want to see how much shear I have on that point, on that given point. Right? So if I wanted to do that based on what I had before, it was like, so I have to go ahead and cut it there. I'm gonna cut it there because this is the interface. I know in the horizontal one, I'm gonna have some shear forces. So I'm gonna cut it at AB. So if I go there and say I'm gonna cut it there. So that's the AB. I'm cutting it at A. So if I cut that at AB horizontally, I knew that I'm gonna have what I would have here. Q, the horizontal shear force. So it's a horizontal shear force. I know that I'm gonna have on that interface horizontal shear force. What was the Q? It was V Q divided by I. The magnitude of the Q was that. Now, remember that I was saying that if I have, if I go ahead and grab an element from there, any element from there, and I look at that element, assume the element, if I go ahead and grab any element, I knew that if I have an element like let me draw it here. I don't want to mess up it. It's going to be there. Draw it here. Have an element, any element. I know that if I have a shear on one of the interface, right? If I know that if I have a shear in one of the interface, when we are talking about the shear, remember that if I have on one interface, I'm going to have on 4 of them. Remember that we cannot have shear only on one interface, on one of the face. If I have on one, I have to have on the all other 4, and they're going to have this formation. Correct? So to be in equilibrium, there should be shear stress on all sides of the element. So if I have it on one, I have to have it on other side. So what does it mean? If I have the horizontal one here, look at here. If I have the horizontal one here, it means that I have to have the equal one on the vertical surface as well. Otherwise, if I bring the element out of there, it's not going to be in equilibrium. So if there's a horizontal, there should be a vertical element as well there. So if I go ahead and again, it's going to draw that interface again. Interface. It's going to be A and B points. So I know that because I have a force here, right? I have a force here, so I have a horizontal shear stress there. So if I have the shear stress there, that look like, if I have a shear stress that goes like this, that seems right. So if I have a horizontal shear stress like that, and whatever it is, I should have the exact same one going down. If this value, assume is the tau average, this value is going to be also tau average. So whatever it is up there, it should be down there as well. Now, if I go ahead and say this is the width of the beam is going to be T, the tau average is going to be, it's just this one divided by T. So it's going to be V Q divided by I T. So the same equation with T. So that tau, so this is average tau in average tau in width at height y. So any question up to here? So just remember that equation, so this is the force in the horizontal plane divided by the width, it gives you the shear, and because the horizontal and vertical shear should be equal, you're gonna have the equal. So that's gonna be the tire. Now a couple of points about them. First of all, the shear, if you have the cross section, the shear is not gonna be uniform in the cross section. So for example, if I have I'm gonna draw that AB. So if I have cross section there, I'm gonna draw it a little bit larger. And that's the A and B. In reality, the shear stress is not going to be distributed like that. The shear stress is going to be higher close to the edges, and it's going to become smaller in the center. So it's going to be, for example, like that here, like that here. And it's going to vary like that throughout the widths. So usually close to the edge is larger, when you get to the center is bigger, but it's becoming smaller. And then that average shear, this one that we are talking about, that is going to be sitting somewhere, for example, here. So that's the average value for the top. So it's somewhere in between of them. Now, if you have for the cross section, that is going to be look like, you get the cross section like this. Then we're gonna name it B and H, which is the B, and this is the H. It says that if B divided by H less than or equal by 0.25, then shear stress in the width can be assumed to be uniform. So, if the height, if the width is much smaller than the height, if I go there and, for example, again, cut it somewhere there. In that case, I can go ahead and assume, you know what, because the width is so small compared to the width, I can assume the shear stress is almost uniform. It's not exactly uniform, but it's almost uniform. So I can say that it's going, it goes from here to here, change very little. And assume it's almost uniform. before. So then it's closer to the average value. That's it. The other couple of points that I want to say that, again, if I have the cross section, like that, and then it's going to be the neutral axis, and this is going to be the y. So at the top surface and the bottom surface, so Q is 0 at the top and bottom surfaces. Therefore, the tau is 0 at the top and bottom. So at the very top surface, the tau would be 0 here. At the very bottom surface, also the tau is 0. So that's the point. So that's the first point I want to mention. Then Q is 0 at the top and the bottom. If the Q is going to be maximum where the Y is 0. So Q is maximum at Y equals 0. So when the Y is 0, when we are actually at the neutral axis, the Q is maximum. So Q is 0 at the top, Q is 0 at the bottom, as maximum at the neutral axis. Okay? So if the width is constant, then tau is maximum at Y equals 0. So this is how the shear distribute along the widths. So it's going to be maximum at the edge and it's going to be minimum at the center. So distributed like that. But in the height, it's going to be 0 at the top and the bottom is going to be maximum at the center. So it's going to become 0, increases to the maximum, and then become back 0. So there are two distribution of the stress. One of them is along the height, and one of them is along the width of that. So in that case, if I want to very quickly draw that, so this is the tau, and this is the y. So the tau would be a start at 0 there, and end at 0 there. width, it will change like that. Maximum right at the center. So this is how the vertical shear stress is distributed in the beam. So previously we talked about how it's distributed horizontally. Now we are looking at how it's distributed vertically. And we're going to look at some special case and then some example. There are two specific cases that we want to discuss them. The vertical shear stress in rectangular beam and vertical shear stress in I-beam, because usually these are the most common shape of the beam we are going to have. It's either the cross section rectangle or the I shape. So we're going to look at it how the shear stress is going to change in those two shapes. So first of all, the vertical shear stress in vertical tall in rectangular section. So if I have a rectangular cross section, let's see what happens. So if I have a rectangular beam look like this, so the rectangular cross section look like that. There's a cross section of the beam that I have, and that's the beam. And then I have the width of the, it's going to be B. The width of that is going to be B. And the height of that is going to be H. And I have the neutral axis right going in the middle of that. Axis. This is H. And then if I consider the Y is going to be from the here up. So that's the Y. And then this distance is C. C is half of the width. Then if I go ahead and want to draw the shear stress on that, I draw an axis here and call it the shear stress, and then I have this axis going up. It's going to be the tau. I know the tau is going to be 0 at the top and bottom surface. So the tau would be 0 here.
You put tau on both axes.
Oh, that's why, yeah. Thank you. I'll fix it. Yeah, the vertical is Y. So we know that the tau would be 0 at the top and bottom surface, and it's going to maximize at the center somewhere. So it's going to become maximized, for example, somewhere here. So the tau would be changed like that. the tau uniform, or the tau, if I want to consider the tau uniform in the height, remember that there are two things. The tau average is the average along the width. The tau uniform is the average along the height. So this average is average along the width. So at any width, if I average it, this is tau average. But if I average it, how it's changing along the height, we call it the tau, I'm going to call it the tau uniform, for example. And it's going to be, for example, somewhere here. Okay, and that I call it the tau uniform. So I just put another name, so I want to make sure that these two, one of them is average along the width, one of them average along the height. I don't want to put the tau average over there. So this is going to be the tau average.
Should this curve be an exponential curve or a logarithmic curve? Or is it its own thing?
Exponential or what?
Like, should it be like like should the two curves almost make like an exponential line, or should they be making more of like a logarithmic line? It's like that's like a parabola on its side, or
exact equation, the exact equation is the, I forgot the name, the power of 2.
okay, good. Exponential. It's not named parabolic.
So in this case, if I want to write them, so I have the tau average, I have the tau uniform, I have the tau max, which is this one here. This point is the tau max. So I want to see how these things are going to be related to each other. So the tau average is VQ divided by IT. IT. So average shear in the width. Then I have, if I go ahead and calculate that based on the formula I have, that would also become tau average for the rectangular shape would become 3 to V divided by A 1 minus y squared divided by c squared. That's the formula for that curve. Then if I want to know how much is the maximum tau, so the tau max happens when the v is 0, correct? When the y is 0. If I put the y 0, it's going to be 1.5 of the VA, so it's going to be 3.2 to V divided by area. And then the tau uniform is the one that we calculated before, is V divided by area. So, the 2 points that I want to make sure that tau average is averaged over, so it's average over width of the cross section, over width of the cross section. uniform. Is average over the height of the cross section. So both of them are average. One of them average over the width, one of them average over the height. But I want to mention that. Look at here. This is the equation we have using it up to here. Shear force divided by area. Shear force. So the shear stress is shear force divided by area. Compared to the maximum is 50% less. So when we are using this equation, we use this equation from the beginning because that was very simple to understand. But if we use that equation, we underestimate the shear by 50% in the cross section. So we have to design it for that, not this. So tau max is 50% larger than assumed uniform shear stress in the cross section. So the one that we've been using it up to this point, that has this problem. Question about the rectangle bit. So the rectangle bit is one of the common one that we are gonna use it. The other one that we are gonna use it is I-beam shape. So vertical shear in I-beam. So I have a I-shaped beam. I want to see how the shear is gonna distribute it on that. It's an I-shaped split. So similar to that, if I go ahead and say, hey, I have a beam, the I-shaped beam, cross section. I have a beam like that, so it's an I-shaped beam. And then if, again, it has the same as the neutral axis there and the same as the y. So same thing as there, the neutral axis and y. The neutral axis. And then I have the y going up from there. And if I go ahead and again start to draw the shear stress here, again, it's gonna be 0 at the very top. So, it's 0 at the top and the bottom. But here, the width is very large, correct? This equation, the IT, the T is big, so the shear stress is gonna be really relatively small there. So it starts from the 0 and goes something like that. It's not, suddenly you shrink the width a lot, correct? So you shrink the width, so the shear gonna becomes really large because the areas become suddenly very small. So the shear is going to suddenly jump all the way to the very high value. And then it's going from there to there. So if we consider the top part, or this part, we call this is the flange. This is the web. So the top and bottom we call it flange, and the middle part the web. If you see, the shear in the flanges are very little. So in practice, we just assume all the shear is carried by the web. Completely ignore the flanges. So in practice, usually assume the entire shear load. So in practice, it is assumed the entire shear load is carried by the web. Just ignore the flanges. It does carry, it helps a little bit, but not much, so we're gonna just simply assume it doesn't do anything. The other point I want to mention that this is the vertical shear stress, correct? So vertical shear stress in flanges might be small, but horizontal shear stress in flanges can be real large, can be considerable. So remember that what I'm talking about is that small in the flanges is the vertical one. The horizontal one was the horizontal. Look at here, the shear stress at the flanges is going to be vertical and horizontal. The vertical is very small. The horizontal might be really big. So don't get confused. Then here we have the tau max. And for the calculus, for the practical purpose, the tau max is as I said. In the web, it's relatively uniform. The change of shear is relatively uniform. So they usually says as the V divided by area of the web. Instead of the area of the beam, I said we are ignore the flanges, so assume the flanges are not there. So if the flanges are not there, it's a very narrow beam. We'll talk about the horizontal one, the horizontal shear stress there later on. Any question? So now let's start to look at a couple of examples, see okay, how we can actually do. So these are the basics of them. So now how we can do the calculation, how we can design the beam. Simple example, simple cross-section beam. So assume I have a beam that look like the wooden beam. So I have a wooden beam that looks like this. The uniform load it's going to be uniform load of 3.2 kips. So this is what we had it also last time. So it's the example we had it last time. Remember that when we did the support reaction, if you had a beam like that, the support reaction was here was negative 0.65. That's the example we did it last time. Let me just very quickly draw that. And the distances here was 8 foot and 4 foot. 8 foot, 4. When we did design that, we came up with the cross section of. So the cross section we had in that example was 3.5 inch, and the height was 14.55, and the sigma allowable. The tau allowable was 4.25 KSI. So we have that. Want to see that if this is, we design it or we work on that based on the average shear stress. Now we want to see if does it work with the maximum shear stress or not. Remember again, if you go back in your notes, we have the shear diagram, and the shear diagram was okay, so it started at negative 0.65 here, and then it goes back down to negative 38.5. It was going up to 4.5. And then it goes back to 0. That was what we had it last time when we worked on that. So the rectangular cross section, how much is the maximum? So this is the allowable. How much is the maximum? Tau max for rectangular cross section. What was that?
3/2V.
Divided by area. And which V we are going to use here? We are going to use the maximum value that we have in the process. So the tau max is going to be 3/2 times the maximum that we have is on 4.5 divided by the area of the 3.5 times 14.55. So it will becomes 0.1325 KSI, which is gonna be less than sigma allowable. So it's less than that. So our design, the last time what we designed it is good because it's less than the tau allowable. So that design we had it last time, based on the equation we used it. It's fine. So remember that we designed it for bending. We designed that. We got those numbers for the bending. In that equation, we designed the beam for the bending. So we find the maximum bending. Now we are checking it for the shear. We designed it for the bending, we check it for the shear, it's working. If we check it for the shear and it doesn't work, so we design it for the bending, we check it for shear. If it doesn't fit, so we have to redesign it for the shear and check it for the bending. Question? Now there's simple problems, simple like that for the I-beam shear. So again, we designed that I-beam shape for the bending. We're going to check it for the shear. See if it's okay or not. So again, we had this I-beam shape. Go back to the example that we designed it, and it has the these 50 kilonewton here. 50 kilonewton here. was 400 pounds. So that was 400 pounds. Foot, and this one is 20 kilonewton. 20 kilonewton per meter. So these are the example we have. And then we have here. It was 52 and 58. The it was 52 and 58. And then the shear guard one we saw it last time. Was looking like this. Start from 52 here up, and then goes down to -8. Then goes down to -58. Goes back down to 0. Goes up to 0. So that was we had for a little bit. Now, again, we designed it for the bending, and we came up with the W360 times 32.9, so that's a cross section we get it, 32.9. So that's the cross section we had it, and the tau allowable is 19 megapascal. So I want to see if it works for the shear or not. So the maximum shear is 58. So I know that the tau max is gonna be the V max divided by area of the web. So how much the area of the web for that? So I have to go to the table at the back of the book. And find it. So if you go in the back of the book and look up the table and look up that table, then the area of the web is gonna be D times T of the web. So if you look at the table, so this is the area, and that area is the entire area. The second column. The third column is the D, is the height. That's the 348 it's going from the very bottom to very top, but because the thickness of the flanges is so small, so didn't ignore it, just goes from the very bottom to top. So that's a D, 348 that you get it. And the thickness of the web is going 5.84. You see, here is the thickness, the web thickness. So it's going down, this one at 3.4. So the thickness of the web, and that's the height of the web. So that's it from there. So these are, did you get it where you got it from the table?
Yeah.
So if you put it there, then max would be 58 kilonewton divided by 232, which if you do correct the units, eventually we're going to get 28.5 megapascal. Which is less than the top alloy. So those, both of these examples that we designed them for the bending, they both check for the shear. So since both of them are fine with the shear. If not, as I said, if not, we have to redesign it first for the shear and then check it for the bending. Usually, if you redesign it for the shear, it will check the bending as well. So these are the two, just checking what we had done before. But let's see what if you are given a shear example. So, okay, go ahead and find the shear or design the shear. So this example, we're going to do it from the start and look at, okay, how the shear would be in the beam. The other two was the continuation of what we had. So if you have the I-beam shape beam, like this, if you have the beam, look like this. That's the point A and B. And there are two forces symmetrical at the center. And then the distances is 0.4 meter, 0.2, 0.4. And the shape for that is, the cross-section shape for that is the I shape, but it's not symmetric I shape. So it's going to look like, just the flange is wider at the top.
Will our table still work for that?
No.
Okay.
Usually you get this kind of beam for the custom design, so there's very special cases that you cannot use those standard ones. is in millimeter, so it's going to be 20, 80, 20, 60, 20. So the information for that are given. So if the C is located there, so the C is located here, and the distance to the C is 68.3 millimeter. Then we have the joint A. There is a joint, connect them together. So basically these are the joints. So these are the three sections like that. So they're connecting like that together. So there's a joint A and joint C. Okay, and so that's the joint A. That's the joint B. So we want to know that if we go ahead and cross section NA here, somewhere here, we call that NN. Also the I is given. The I for the cross section is 8.63. 8 point. Meter cube. Then we want to know that tau at A and tau at B at section NN. So it's what we want to know. How much is the shear stress at the A and the B at cross section NN at that point? If I cut the beam at NN, what's the shear stress at A? What's the shear stress at B? You got what's the question? So I cut the beam at N. So I'm not gonna look at the maximum one for any reason. They say, okay, I don't care about where it's gonna be maximum. Cut it at NN, and then tell me how much would be the shear stress at that point. And there. And you probably just looking at that, you know that it's going to be 1.5. And it's going to be 1.5 because it's symmetric. Okay. Work on that. So if I go ahead and cut it there, if I go and say, okay, I want to find the internal shear. So find V at NN. So if I cut it at NN, okay, that's my beam. I'm cutting it at NN, and then what I have is that it's going to be 1.5 here. Then I have the P, which is going to be the 0. Then I have the V, and then I have the M. Okay? So sigma Fy is 0. Therefore, the V is 1.5 kilonewton. Agree? Now that I have the V, I can go ahead and find it for the joint A and joint B. So first of all, joint AA. So let's look at the joint AA. At joint A. I'm going to redraw the cross section. So if the cross section is there, if this is the cross section that I have, I want to find the joint AA. So the joint AA is here, correct? That's the AA. I'm gonna cut it from there to see what happened there. So this distance is 68.3. Remember, I need the first of all I need to find the QA, which is going to be the area of the A times y bar for that area. So how much is the y bar distance from the neutral axis? So it's going to be this distance, correct? I'm gonna put it there so so this distance is the y bar. So how much is the y bar? So it's a 40 from the center of so it's not there. I have to put it up. So it should comes out to yeah, we should get 41.7. Do you get that? So the total height is 120, correct?
Mhm.
Minus 68.3 minus 10. Does it come? Does it come to 41.7?
Yeah,
it should
it
come
does.
out to 41.7 anyway. So the Q at A, what's the area that I'm looking for? The area is, correct? This is the area that I'm looking at. So that's the area of the A. That's the area. I'm looking at the area on the top of that where I'm cutting it. Remember that? I cut it there, so I'm looking at the area above the line I'm cutting it. So the Q at A would be the area, which is going to be 100 by 20. That's the area of that, times the Y, which is going to be 41.7. Would be 83. So the Q Q at A would be 83 times 83.4 times 10 to negative 6 meter. Now the tau average, what was the tau average? VQ divided by IT. So the tau average, the V is how much? 1.5 kilonewton. 1.5 kilonewton. That's the V. The Q is 83.4 times 10 to negative 6. I is 8.63 times 10 to negative 6. And the T, how much the T? 0.02. Okay, it's a 20 millimeter. It's going to be 0.020. So the tau average would be 725 Pascal. The same is the very same thing for the joint BB. So if I go for the joint BB, I'm gonna redraw it again, draw cross section again. That's the cross section. And this time the BB is here, so I'm gonna cut it there. I'm gonna cut it there. Again, the centroid is 68.3, and this time I need the Y. So look at here. Is there? I'm cutting there. I have two options for the area. The Q, I'm gonna call it. So the Q at B is the area of B times Y bar. Look at here, before right. For the area I have two options. I can consider the area above the line and below the line. Always I have two options. Here, it's easier to take the area above the line because it's a single area. When it comes here, it's easier to consider the area below the line. The Q for either of them is equal. It doesn't matter. If you calculate the Q for the T shape of the top, would be equal to this small one. The same here. If you calculate the Q for that, it's going to be the same for this one. So usually, when you cut it, look at the area above it and the area below it, see which one is easier to work with. Here it's easier to work with the one at the bottom, so I'm going to choose this one, and then this time this is going to be the Y bar, and the area of the B that I'm going to select is this one. So how much the Y bar here?
58.3.
So this is 68.3 minus 58.3, correct? So the Q at B would be the area of that bottom part. This time is going to be 60 times 20 multiplied by 58 times 3. So Q at B is 70 times 10 to negative 6 if you convert it meter cube. I'm gonna just make this y1 and y2 so you don't get confused between them. So I assume this is y bar 1, this is y bar 2. So you know that. Don't get confused. Assume these are 1. No, these are 1 and 2. Now that I have the Q, the tau average is the same as that. So it's a VQ divided by IT. So the tau average would be, the V would be the same. So you go to 1.5 times 10 to 3. The Q is the one that's changing. It's the 70 times 10 to negative 6. The I 863 times 10 to negative 6. And the width is also the same, 0.020. So the tau average would be 608 kilopascal. Question? The next problem, well, I don't know if we can get through that or not, but the first part of that is drawing the shear and moment diagram. First, let's go and do that. And then the first problem is actually a design problem. So it's given us a beam and says that, okay, go ahead and design that, correct? So just to save the time, I'm gonna do the shear diagram, moment diagram right now. So when the next time we started, we already have the shear diagram. We only focus on the design part of that. So we don't need to spend time on the shear diagram and the moment diagram. So it's a wooden beam, and it says that, okay, if you have a wooden beam, look like this. And assume we have a simple support. So we have simple support here. Then, and there's 3 concentrated load. One is here. One is here. One is here. And it's gonna be 2.5 keeps. It's 1 at the center, and again 2.5 here. And the distances between them is 2, that's a 2, 3, 3, 2, so it's a 2 foot, 3, 3, and 2. Like that. The cross section that it has it is 3.5, and the D, if you don't know how much is that, the sigma allowable is 1800 psi. And the tau allowable is 120 psi. So we want to know, we want to design it for the D. So this case, we have to go ahead and check it for both shear and the moment. Okay, because we want to design it, we will have to make sure that it doesn't fail under the moment, it doesn't fail under the shear. So this time, because it's a design, we have to go ahead and draw the both shear and moment diagram, so we know what's the maximum shear in the beam and what's the maximum moment in the beam. So we have to do that. So for the first thing we need to do is the reaction of the support. It is the symmetrical, so it's gonna be 3 and 3 on both sides. Now I have to go ahead and draw the shear a moment. So I want to draw them. It's going to be shear. And then there's a moment. So let's just bring down these points. So let us start from the shear. Shear at point A. Is A. And then the other point. So shear at the A. How much the shear at A? 3. 3 positive. 3 we are going up. So we are going 3 up. Plus 3. Then when I go ahead and get to the next point, it will push it down to what?
Half.
2.5, yes. So it's gonna becomes 3 minus 2.5. That's gonna be constant. When I get to the next point, it's gonna push it again 1 down, so it's gonna be 0.5 minus 1, so it's gonna be negative 0.5. It's gonna constant. Then I get to the next one, it's gonna push it down to negative 3. So it's at negative 0.5, negative 2.5, negative 3. And then you push it back to negative 3 plus 3 would be 0. Agree? So that's the shear. Now about the moment. So if I want to find the moment, I have to go ahead and calculate the area under each of these. There. So how much the area here? So it's a 3.2, so it's going to be positive 6, correct? What's the next one? It's a half times 3, so it's going to be 1.5. So it's a plus 1.5. The next one is again negative 1.5. And the next one is going to be negative 6. So now we get to the moment. How much the moment at the A and at the B?
0.
simple support at the end of the beam, the moment will be 0. So I have to start from the 0 and I get to the 0. So that part I know. So next is that I'm going from 0, added 6 to that. So from 0 to the 6. How I'm gonna go up? Linearly, because it's constant. So the next one is gonna be linear. So I will go to the 6 linearly. So it's got the 0 plus 6, which is 6. Then from here to here, again it is positive. So still I'm going up. How much? 6 plus 1.5. So I'm going up. And I'm going up linearly. This means it's going to be 6 plus 1.5. This is going to be 6.5. Then here's negative. So I'm going down. Again, how I'm going down? Linearly. Correct? Means linearly I will go down. So it's going to be 6.5. So it's going to sample. 7.5 minus 1.5 would be 6 again. And then from here, 6 minus 6 going down linearly. So it will go back to 0. So it's going to be 6 minus 6 would be 0. Agree? So now I know what I need to know. What's the maximum M?
7.5.
It's a 7.5. Keeps foot. Or because we want it in the inch, so it's going to be 7.5 times 12. Keeps inch. It would be 19 keeps inch. So that's the moment. And so this is foot to inch. And the maximum shear is
6. Oh, 3.
3.
I was looking at the wrong.
So now I have the maximum moment and I have the maximum shear. So now then I can go ahead and start to design it. So keep that up to here. So next time I will start from there. So I know the maximum moment, I know the maximum shear. I'm gonna design the beam for those numbers. Question?